Yeah, very much. My pleasure to be here, and also thank for the organizing committees for giving me the chance. I think it's really my great honor. Also, although at least in this tough period, I still strong believer research collaboration is still going on, and so this is something that make us even stronger after the pandemics. So this is something I really know when a few years ago we talked about how we can really NTU, KAIST can work together. So I would say this is something very good kind of starting point. I'm really looking for more potentially, not only potential, I mean real collaboration like what between Seoul and with me, we have one joint in kind of a PhD exchange already, but we are really looking for more collaboration because the student was here for half years, really kind of very fruitful and also very kind of integration with our students, and it still keep very kind of long-term this kind of relationship even today, keep exchanging emails and so on. Yeah, my pleasure. Okay, and today I want to show you something what we are doing in NTU in these years, especially how apply the electronic scheme for the sense digitalization. So this is something we are exploring for a few years already. And this is something the one we are looking for. Now we need to go back, what's this kind of sense digitalization? In fact, humans have 5 senses. So this is everyone well known already in terms of sight, sound, touch, taste, smell. But if you really look carefully, how many of these kind of sense can be digitalized? Still, yeah, some people are still working on it, but still some of it is still not. Like for example, taste and smell is a very challenges. So that's something one we just as a material science, I just curious how can digitalize it? Okay, it's kind of digital signal, and then you can really convert into something useful application. The second interesting is not just in digitalization. For me, I just curious from science, from kind of entertainment issue. We talk about a lot of 6 sense, right? It's a real ability to perceive something that the parents is not there. Now you can imagine, right? If I can really digitalize 5 sense, in one day, I have a 6 sense for sure, right? I can really have this kind of data science, do this kind, all this kind of sorting, analyzing, feedback. Even more, maybe not only 6 sense, 7 sense, 8 sense may even come out. So this is something I kind of, as a curiosity, I'm asking myself. So that's something we start our direction. And so this is overall in terms of research vision for my group. We want to converge mind and the matter. But here, we want to converge physical and the digital technology. For matter here, more related to this physical world. There are a lot of this kind of material science, this kind of electrical and range device, a lot of this kind of capability we can do, can build. Another side, digital world or mind is kind of data, but the way you can already kind of display very quick, linkly, but how these two can link together. So this is something we are doing. We try to build this kind of conformable interface based on material science capability to address issue like just the previous 2 speakers mentioned already, the mechanical mismatch, and also the interface of his issues, and also other kind of issues in terms of material science. But not only this one, because in the end you go to a device integration, interconnecting, interface problem, always go with us. So that's why material science is kind of fundamental way to get reliable biological signals to address issue about its kind of fidelity, sensitivity, stability, and continuity. In the way we talk about long-time monitoring, long-time signal capturing. So once this is something one can address, I think this is something where material science can play a very important role there. And then we can move for next step, how we can really digitalize, translate the biological signal, because mentally the biological signal is kind of analog. But digitalized signal is kind of 0-1, it's kind of digitalized signal. So that's something one in electrical engineering side, they can really figure out a way how can do this kind of analog digital transition. Even this is something a small kind of experiment in our lab right now also. It's the best of our data. And then once you get the data, then you can involve artificial intelligence, data scientists together to this kind of data mining, and then to even can link with the current one. A lot of people talk about this kind of neuromorphic computing. So this something one can really merge together. And the end can build one we call e-sense, so electronic sense. Okay, so this is the way how we can really link the physical world with the digital world, and then to build something beyond our human capabilities we have done. Okay, so this is something in overall just show you what our aiming, vision, and also philosophy behind. Because by this workshop, I hope we can more kind of discussion, interaction, maybe can work more intensely together in this related field. Now, today I just show one skin. So the electronic skin is kind of one we get inspired from human skin. Human skin is kind of largest organ, about 2 meters square. But human skin play very important role. Although it's a very simple organ, if you compare with heart, compare with lung, simple organs, but play very important role in this kind of sensation, regulation, protections. So this is something one is kind of become emergent people to think, oh, how we can really get kind of inspiration from skin to build this kind of so-called electronic skin. So this is something one really draw a lot of people attention, not only from material science to build this kind of flexible materials, from electrical engineering side can build this kind of flexible, stretchable electrodes, circuits, and also for healthcare, they really want to have this kind of wearable or this kind of impassable device, really do some continued monitoring to really do early alert, rather than always you send the patient to the hospital. It's always too late. So that's something, especially now today, for the world become aging now. A lot of elderly people stay at home. You need this kind of continued work with this kind of wearable device to really help this kind of early alert rather than last minute. And also prosthetics, and also even social robotics, because again, this is also related to the world. You can see now today is becoming aging. Now you need more this kind of robots, social robots to replace the nurse. But I believe, as elderly, right? I mean, you always say, oh, this is something easy to broke, or the interface is kind of very frigid. Okay, if it's broke. So in this case, you want a robot, not made by metal. You want robots really like a human, this kind of human skin like. So that's why this is something electronic skin also play a very important role in this kind of social robots and to help for our people. And then it's due, right? I mean, in this is 15 years, this field is kind of really interesting. And then people start from sensing, capability development, go for this interface build up, and then manufacturing, and also integration. You can see every 1 week, you always see some of breakthrough publishing somewhere about the electronic skin, flexible electronics area. So this is something I would definitely, this is something kind of future. But I always mention for one material, one device, one technology, want to be more kind of long lifetime importance, it must have industrial acceptance. It means that your technology, your fabrication must be accepted in industry. Otherwise, no future at all. So that's why the question is, how can develop this kind of protocols can be industry acceptance rather than just publish paper. So this is something one really curious us. So that's why today I will show you maybe quickly mainly focus on first parts. How we can fabricate this kind of conformable bioelectronic interface. So this is exactly kind of, it can align with the industry kind of protocol, and then can be quickly accepted by industry through this kind of fabrication and also scale up. So if I mentioned already, for electronic skin, very challenging kind of mechanical mismatch. Okay, so this is something usually for the device with the interface, because different kind of mechanical issues there. And the leading problem is kind of the signal noise is very high and also easy to peel off. So this is something one, because like nature, this kind of mechanical issues there. And then why we need to address the issue there. Take example for this one. So this we put it on electrodes on skin. If we don't have this kind of flexible stretchable electrode like this one, this is the kind of column market or clinical use ECG. These electrodes cannot stretch, although it can really adhere on the skin, but it cannot stretch. In this case, we will stretch our skin, the so-called surface interface potential will drop. Okay, so this is something the typical conventional electrodes, you can see it. So that's why you want to build this kind of interface. You must make sure this kind of electrodes can be stretched and also conformable, allow have this kind of when you stretch the skin, the device also have no change at all in this kind of surface potential to really ensure the signal change is because of your body somewhere kind of potential change. It's not because of your system problem. So that's why on-skin electrodes is very kind of fundamental, how to make this one stretchable, conformable. In fact, not only about skin, in different positions. And I really like this picture by Dayon from Seoul National. And he really illustrated all this conformable bilateral interface in different kind of applications, from brain, from heart, from skin. This is something a very kind of important field to relate. But few issues, you want to make this kind of application going on, stretchable, the previous slide I mentioned already, but also reliable, durable, kind of long-term monitoring. Reliable means you really make this reliable signals. So that's why the fabrication still challenges, especially how you can get this kind of industrial acceptance, this kind of process. Like this is slide to show, in fact, Zhenam, John, and also other people really spent a lot of efforts to build different kind of structure. Like a previous speaker also mentioned about intrinsic material, intrinsic semiconductors, suspended structure mainly come from John's group. Different strategy can do it, but still, the way how can we develop this kind of approach can be widely accepted by the kind of communities and challenges. That's why I want to the community. In fact, we can do it now. So this is something what we call thermal radiation assisted metal encapsulation. So this is the one way to form highly stable and stretchable conductors. The process itself is simple. If you just deposition of metal onto the PDMS, people always know that metal is easy to peel off. This is challenging, so that's why a lot of people didn't really apply this one. But we solve this problem is, instead of using the fully polymerized PDMS or fully cured PDMS, we use half cured PDMS. It means this PDMS here, just about 50% polymerized, still remaining about 50% monomers. Then we do the thermal deposition, because metal can re-evaporate and then can penetrate into this half-cured PDMS. Because of remaining thermal radiation, because during thermal evaporation, you have this kind of thermal radiation there. We use this thermal radiation to further polymerize unpolymerized PDMS, or this kind of monomers there. In this case, the metal will encapsulate inside. So this is some kind of thermal radiation assist metal encapsulation, and then you can really continue this kind of evaporative. You can get this kind of continuous metal films. So this is something the simple process. So that's why we name it trap, T-R-A-P. It's kind of trap. You trap the metal in the polymers. So this is something how it looks like. Okay, this is the polymer. Okay, and this is gold. It's stretchable gold, bendable, foldable, and then it really kind of stretch it as well. And then you can see the back layer color is kind of black color. Why black color? Because gold and particle aggregate together in a PDMS. So that's why it's kind of black colors. But in the top layer, it's kind of gold color because it's kind of conductive. So this is the process. And then this is a big picture. But if you see how it looks like, okay? So surface itself is kind of rough. It's like our skin. You can see exactly like our skin here. And then the skin will have this kind of wrinkle structure because it can be stretched. In similar case, we have wrinkle structure here. So that's can be stretched as you want. And also, the cross section here is multiple layer structure, like a skin exactly, right? Multiple layer structure. So this is something that allow this kind of electrode to be stretchable and also very stable, very difficult to peel off, like this more so. So we do 3 experiments. First one is metal on glass. The second one is metal on PDMS. The last one is use our trap. You can see, use the previous 2 approach, just Scotch tape, easy to peel off. So this is something the big issue later if you don't solve the problem. But use this trap approach, trap electrodes. You don't have this issue anymore. It's very stable in a way you can make this kind of larger scale. Yeah. In all these steps, just take about less than 1.5 hours. You can get this kind of stretchable, larger scale, this kind of conductive electrodes. But of course, what's the reason behind? The reason behind, in fact, is JKR adhesion series. So in fact, this is kind of well known already, especially if you talk to AFM related. But in here, in fact, what they do is we increase contact area between the metal with the polymer. So that's why it kind of mechanical interlocking inside. In the meanwhile, because the metal with this PDMS have this friction, so 2 part together to really enhance interaction between the polymer and the PDMS. And all this fabrication is in one process. And then Now the question is, for PDMS, a lot of people know already, for PDMS, once it's kind of cracked, you just apply certain force, the crack easily migrate. The scientific reason behind is because the fracture toughness, okay, GC here, the fracture toughness. For PDMS, the fracture toughness is pretty low. So in this case, the crack easily migrate. Once I just kind of calculate, it's like for a surgery, right? You can just kind of cut and easily migrate. Then how do you avoid this kind of issues? Have this kind of anti-crack formation or this kind of anti-tear electrode formation? The answer is simple or straightforward. So this is something we worked with the Zhenan group a few years ago. So her group have this kind of UPY, this kind of self-healing polymers. The stretchability almost more than 20 times. This is something about very good. And then we just simply use our trap approach to deposit our metal on this kind of simple molecular polymers. And then we can get this kind of stretchable anti-tearing electrodes. So this is something one offer high stretchiness, toughness, as well as stretchable. So the reason behind is because fracture toughness here. This is PDMS, fracture toughness. And for simple molecular polymers have 3 times maybe higher than the PDMS. So that's the reason it works. So as so by this way, you can see the purpose cut it, but the crack didn't migrate at all, just stretch. And we still feel further cut it. Electrode just migrate and can't stretch, no migration at all. In fact, at the end, we use this experiment for this kind of animal long-term monitoring. It's really successful. We monitor the EMG for more than 1 hour, can get this kind of reliable data as well. So the trap approach itself, not only for the film, we also can use this kind of mask to form this kind of electrodes. And also we can use this kind of, we combine with our this kind of printing process, also can get this kind of pattern electrodes. So this is something one electrode we also now is using for this kind of rehabilitation related this kind of project. It's very kind of very successful. Hopefully next time I can share with you the data. The very beautiful data to really allow we digitalize the muscle signals and control prosthetics. And of course, this is also coupled with the AI together. Okay, so I talk about issue about stretchable electrodes, how we fabricate. And this approach is really kind of industrial acceptance approach. It's really aligned with the CMOS technology. We don't have any kind of special kind of equipment needs. So this is something that I would really encourage the community. If you really want to use this approach, let me know. We can do our best to help. And then moving forward, stretchability is just one issue. There are more than stretchability. For example, biocompatibility, reliability, durability. All these are important related to this kind of bio-interface devices. In the last few years, we spent also a lot of efforts to build this kind of biocompatibility issues. For example, we developed this kind of plasticized silk. So this is something that FDA approved this kind of interface polymers, and kind of biopolymers. And this is something we interface electronic device to build this kind of stretchable and also biocompatible electrodes. Another part, we also put a lot of efforts this year about this kind of reliable issue to really how to really adjust this kind of signal, make sure you get a high signal, and then especially under this kind of wet condition, because Singapore, you really put the wet on skin. This is always generate a lot of this kind of threat. The threat, more threat, it means electrodes is less stable. But in fact, we figure out another way is more threat, electrodes more adhesive. Then maybe let me show you how to do it. Okay, maybe next. Okay, so this is slide. So this is something about plastics, silk proteins. We use as substrate to fabricate this kind of stretchable electrodes. So here, the main issue is you want to lowering the Young's modules of the silk protein. For silk protein, mostly in terms of Young's module is more than gigapascal. But for our skin, it's about megapascal, even kilopascal. So this is something about 3 to 4 make this difference. So what we do is we're adding with our metal ions and other kind of small molecules to really break up helix and beta shear structures to make all the structure be more random coil. So this is the way it's effective to really lower down the Young's modules. And then we apply our TI, the trap approach, to deposit our metal on top. So this is the end, we can get this kind of stretchable gold electrodes on the silk substrates. So this is how we do it in principle. And then, but this is something one can continuous film. Okay, we know already. Once you cover the plastic on your skin for a long time, you don't feel comfortable because you are not allowed this kind of metabolite or this kind of water evaporate out, and this is don't have this kind of gas change. So that's one. We based on this approach, we further modifies use this kind of electrospinning to make this kind of porous electrodes. It's kind of stretchable porous electrodes. And then now allow this kind of gas in, gas out. So this is something we want to get this kind of low evaporative resistance in highly conformal electrodes, especially under sweaty conditions. You can see. So this is a slide to show you 3 electrodes here. This is the clinical electrodes. Metal. This is the gold film. This is gold on silk. This is the PP1, like a polymer. This is should be should be the conductive polymer, conductive on the silk. But this is silk, you kind of electrospinning. So this is before exercise. Okay, all skin is about 31 degrees. Now after long time exercise, about 1.5 hours, you can see for this side, the skin temperature increase. But for our this kind of metal porous electrodes, you can see the temperature still as our skin, 32 degrees. It's really kind of, you didn't have this kind of heat kind of encapsulated there. So this is the way to do it. And not only about this one, and also we can do this kind of long-term this kind of monitoring. So for example, for treadmill test. So this is a well often used for the heart disease monitoring. A lot of people have this kind of heart disease problems. And then if you go to see the doctor will wear you 10 electrodes to make 12 lead ECG. But the question is the electrode itself is GP off. So that's why the nurse always use kind of tape to ensure they will not fall down. But this, it's not very comfortable enough. And then we change this, the reason behind, because more humidity, less adhesive of this electrode. So this is for conventional, look like this one. And then we change this system to the PP1. Okay, use this our silk electrode as well. And then on a white skin or white surface, electrode is really adhesive. And our discovery is this one. More humidity, our electrode is more adhesive. It's much better than conventional electrode. So this is exactly kind of reverse direction. So this is allow us to do this kind of device for long-term monitoring, especially for sports, right? Sports about 1.5 hours. How do you know this kind of status? The answer is yes. You can see this electrode is really kind of deformable, different state, rigid, original squeeze. You can see the very good kind of signal repeat there. And also in long-time monitoring, we run for 1.5 hours. The red color is our device. The blue color is the clinical device. You can see after 5 hours, you cannot signal anymore. But for us, it can really run for 1.5 hours. So this is something we want to show you movie. So this kind of variable device on skin, and then with our black color is our electrodes. These all are values in Bluetooth transmit the signal to the cell phone. This is allowed for this kind of long-time monitoring, as the previous slide showed already. You can see the signal pretty stable there. Okay. And not only about this kind of skin, it also can use for this kind of water also as well. You can see we can put the electrode on water, on the skin, and then to trim, and also can do this kind of computer monitoring. So this is potentially useful for this kind of aquatic ECG monitoring. So this is something related to the modern lifestyle. People want to go to the water. So this is fortunately can be used. Okay. So maybe another 2 parts I will quickly jump, okay, to share people how we can digitalize biological perception, action, and also extend human sense. And for example, Pierre mentioned already, our electrodes very kind of different electrodes, very high sensitivity. The reason behind is because we have low impedance and also high adhesive. So this is usually our electrodes. Now we can digitalize this kind of muscle signals. This is here, you can see we have put 9 electrodes here to really each electrodes, few electrodes control one muscle and then can mirror in this parts. Okay, so this is something we want to digitalize this kind of muscle signal and then convert to electrical signal control prosthetics to do this kind of mirror, exactly mirror. Okay, so that's why this is electro how it looks like, very mirror, and that means very precise. We can get signals, but you see the commercial electrodes not work well. You can see the commercial electrodes in terms of signal very weak, but also a lot of problem with crosstalk, and then cannot get this kind of signal precisely enough, and to get this kind of signal to convert with robot prosthetics. But we can do it because our low impedance and also adhesive there. And then and also further moving on, we also really combine with our this kind of for the data. First of all, we combine strength sensor here with this kind of somatic sensors, plus this kind of visual sensor together, coupled with artificial intelligence together. Then we can do this kind of multimode fusion to inspire from human. So this is something we call the BSV associative learning work. This is something is the last year work. Combine the two sensor with the AI together. Again, this one can allow us to work on this kind of high accuracy. Our approach is almost 100%. So this is something exactly kind of strength sensor coupled with the vertical sensor. Again, this is demonstration used to control robots. Just show you how accurate it is. And yeah, so this is basically the science behind. It's a data fusion plus with AI. If people are interested, you also can read paper there. And then also we can extend human sense. For example, artificial olfactory resistance. And then we learn this artificial olfactory resistance. And then we build from here, we build a sensor, build our data, and also combine with AI, and then can build this kind of artificial olfactory resistance to really mimic our nose to do this kind of smell. This is something we use to smell the freshness of meat. I would say this is also the one to really beyond this kind of human capability, it's the human sense. And also we can apply in our electrodes, not only about in our animal world, in plant also, we can build this kind of conformal device to communicate with the humans, between humans and plants, and to really control the plants. So this is something also a lot of projects also ongoing on, because we feel plant electronics is also kind of the next generation potential there to really to build this kind of harmony nature. So that's something one we are doing now. Yeah, but of course, this is something still need more collaboration with the people in the field and to really push on this direction. But here, if people interested, also can read these papers as well. Yeah, I think I strong believe sense of the world, perceived future, it could create endless possibilities. And then the similar case of collaboration. If you have collaboration, you also create endless possibilities. Finally, thanks to my students, thanks to my funding agency, also thanks to my collaborators. Thank you very much for attention. I'm happy to take any questions if stay healthy, still connected.
Okay, thank you, Xiaodong. So I think I really enjoyed your last part of the talk. So you are now applying some machine learning and artificial intelligence for your sensings. So especially for the smell, yeah, I always has the question that, yeah, maybe so how is it close to humans? The smell response or your system? I mean, what's your perspective? How close is
Yeah,
it?
I would say if you go for particular systems, it's very close. It also even might be better. For example, when we distinguish the meat freshness, the performance is much better than human. This is something where we can do this kind of autonomous systems as well. But human is more kind of complex. We can distinguish many kind of gas. But for my systems, only one type of gas. So this is something one kind of gap there. But I would say it's always kind of gradual, steps by step. And then one day you really can mimic our kind of sense, and then can really create a lot of devices much better than human. And then because you can see, in fact, a lot of projects are now also try to really address the disability issue now for a disabled person to really reconstruct the capability.
So in one sense that, I mean, if somebody sees something, they feel, smell, or sometimes they hear voice, right? So yes. What you told here today is like 5 senses, they are all connected, and then they can get those senses together and then combining certain human experience. That will be very interesting future topic.
Yeah. It's basically my idea, but this is something one need a whole community work together. Due to efforts very big.
Yeah, I hope I believe you will make it. Thank you for the great.
Okay, thank you.